Watch this violet fishing lure break the water's surface. Even under the blinding midday sun, the color seems impossibly bright, practically generating its own light. Daylight fluorescent pigments operate as a photophysical engine, engineered to absorb invisible, high-energy ultraviolet radiation. Once absorbed, an electron briefly jumps to a higher state, vibrates, and then releases a longer wavelength visible photon. You're seeing normal reflected light, plus a bonus emission of extra color. This intense artificial brilliance relies on a specific set of environmental conditions. It only works because our atmosphere is absolutely flooded with ultraviolet energy radiating from the sun. Take away that specific band of solar energy, and the visual effect collapses. The lure is an optical parasite, entirely dependent on a rich atmospheric host to survive. The moment that lure dips back below the surface, the rules of atmospheric physics end. The air-water interface is a harsh, immediate boundary line. Above the surface, light travels freely through clear air. Below it, the water column is a thick, dense soup, packed with microscopic suspended particles, dissolved organic compounds, and the water molecules themselves. As the lure descends, its engineered glow enters a race against depth. To maintain that vibrant violet color, high-energy UV light has to penetrate the water and reach the pigment before the energy is completely extinguished. We are entering the photic zone. Here, human engineering takes a back seat, and the physical medium of the ocean begins to strictly dictate exactly which colors are allowed to exist. The rate at which light disappears is governed by the Beer-Lambert Law, specifically a mathematical variable called the downwelling diffuse attenuation coefficient, known as KB. This coefficient represents the primary variable of extinction in any water column. This extinction is driven by two destructive forces. The first is scattering. As photons travel downward, they ricochet off suspended particles, fracturing the light beams into chaotic, random directions. The second force is absorption. This is a thermodynamic process where the water molecules and suspended matter physically swallow the light energy, converting those photons into heat. Combine absorption and scattering, and you get KD. It creates a harsh mathematical gauntlet that every single wavelength of sunlight must attempt to pass through. You can see these forces acting on the lure in real time. By the time it passes the 5-foot mark, the constant ricochets and molecular absorption have already begun to strip away its violet intensity. But the gauntlet doesn't treat all colors equally. The primary driver of short-wavelength extinction is a complex mixture called chromophoric dissolved organic matter, or CDOM. Originating from decayed plant and animal matter, CDOM acts as a microscopic dissolved shield. It is uniquely tuned to absorb short-wavelength ultraviolet rays exponentially faster than it absorbs visible blue or green light. This graph charts downwelling irradiance, the amount of sunlight penetrating the water, measured at various depths off the coast of San Diego. Look at the left side, between 300 and 400 nanometers. This is the ultraviolet range. Notice the massive collapse in irradiance between the surface and just 10 meters down. The UV light is being eradicated. Now compare that to the center of the chart, in the 450 to 550 nanometer range. This is the blue-green transmission window. Even at 20 and 40 meters deep, these wavelengths maintain relatively high energy levels, slipping right past the CDOM shield. The data reveals a harsh truth for our fluorescent lure. By the 10-foot mark in most coastal waters, the UV spectrum is effectively erased, regardless of the sun's intensity at the surface. Descend to 20 feet, and the visual environment is stark. The lighting shifts into a monochromatic wash of surviving blue and green wavelengths. Look at the lure now. That screaming violet aura is completely dead. The vibrant color has been replaced by a flat, dull gray appearance. This is a total biophysical failure. Fluorescence is a pay-to-play system. If the water's CDOM and suspended particles absorb the ultraviolet light before it reaches the pigment, there is no excitation energy left to trigger the glow. Zero UV input means zero visible output. 20 feet down, the lure is a heavily shadowed object, stripped of its engineered advantages and surrendered to the physics of the medium. The practical consequence is immediate. A predator, hunting in the dim light, registers nothing as it swims directly past the lifeless lure. The contrast it was designed to project simply isn't there. It doesn't matter how meticulously an object is designed in a laboratory. The downwelling diffuse attenuation coefficient is the final judge of what gets seen. The exact concentrations of dissolved organic matter and the local biology hold total jurisdiction over the visibility limits of every aquatic ecosystem on Earth. You cannot cheat underwater physics. You can only hope to understand it and work within the narrow spectral window that the water allows.